All right, so here we go. So we're going to start off by talking about what equilibrium is. Now, the key here, and we kind of talk about things being equal. Well, the problem with that is you got to refer to exactly what's being equal and then how things work. The problem is the concentrations don't necessarily have to be equal, but can they be?
Sure.
Yeah, the key here is that the concentrations are actually constant. They're not going to change. But the key is they're constant over time. So no matter what's going to change, they're going to stay constant. Not equal, potentially equal, but most of the time they're not. It's just going to remain constant. Now the key here is also that on the molecular level, there's a frantic activity. I used a different word. Does anybody remember that word?
Static.
No. I can never spell this word. Chaos? That's C-H-A, yeah, that's how it's spelled it. Yeah, chaos.
Chaotic.
Yeah. Okay. But equilibrium is not static. And what does static mean? Still. Okay. Equilibrium is not still. It's constantly moving. But what's the problem with us and equilibrium? And those last two little bullets.
The Earth doesn't like to be at equilibrium.
No. This right here in this blue box. Can you see that? No. That's the problem. Okay, the molecular level is going crazy, but you can't see it, and that's going to be the biggest issue. Next, again, this is what I always say is macroscopically. What is macro? This is with our eyeballs. Okay, our eyes, it looks static, and again, we've already said static stands for still. But again, microscopically, down on the atomic level, it is chaos. Just pure chaos is reigning. Now, I showed y'all that little animation with the ants. Do y'all remember that? Where one ant picked up a stone, and it carried it to the other side. But at the same time, one ant was carrying, what was the other ant doing? Carrying one the other way. So, again, we talk about the rates being equal, and that's it now. Okay, but first of all, these are the types of graphs that I want you to get used to reviewing. The big thing is, if you did not see this reaction, and you did not see those things right there, the actual species, could you still determine which line was what side of the reaction? And what I mean by that, reactants versus products. In all reactions, not all, in most reactions, what do and again, notice what the axes are, the concentration, what do the concentrations of most reactants do? They decrease. Well, how many lines are there decreasing? 2 of them. So you've at least got 2 reactants. Now, if you look at the balanced equation, it's obvious. But do the 2 lines that are decreasing decrease at the exact same rates? No. How can you tell? Say it one more time. The slopes are different. Not only are the slopes are different, did they start at the exact same concentrations? No. Notice which one started at a higher concentration. Hydrogen started way up here. Nitrogen started way down here, so they started at different concentrations, and their slopes are going to be different. What causes their slopes to be different in their rate of change? Very good. So for every 1 nitrogen that's used, how many hydrogens are used? 3 of them. Okay, so that's going to cause a drastic change in their rates, because for every 1 nitrogen that you throw out, you've got to throw 3 hydrogens, and so that's going to make it burn a lot faster. So if you were somehow able to take the slope of this part, matter of fact, let me redo that. Well, maybe I can't. Let me just change color. If I were to take the slope at this point, first of all, AP or pre-calculus people, algebra 2, how do you take a slope of a line that's curved? Thank you. You got to take the point tangent to the curve, right? What part of math is that? No, it's not. Y'all haven't got to that? Joanza, do y'all do this? Yeah. Okay. He's my only AP Cal kid, so I got to sometimes bounce things off him. So you got to take the line of a tangent to the curve. Now, when you take, can y'all see that, or is that too hard to see? All right, let's change it to maybe this orange. No. Blue. That better? There you go. Okay. All right. So what we're going to do is we're just going to take this. Now, what is slope? Basics. So basically you're going to determine the rise, you're going to determine the run, and that will give you the slope. So really, in chemistry, the rate, we know it's rise over run, but what is the rise in this particular part? It's the change in concentration over the change in what? Change in time, delta t. So that's how you can find your rate, which goes back to kinetics as well. Okay? All right, next slide. Go to the end. I want you to try to recreate this graph on the top left one. Just sketch it down real quick. And the point that I want you to see is when does this react, and I should have mentioned this while I was here, when does this reaction reach equilibrium? No, that's fine, yeah. When? When the lines flatten. Is that a word? We're going to make it one if it's not. When the lines flatten out. That's how you know it has reached equilibrium. Okay? It doesn't have to be perfect, but it's the point at which the lines eventually kind of level out. So here, this goes back to the very first slide. The concentrations, do they have to be equal? Are any of those concentrations equal to equilibrium? No, but they're what? Constant. So that's the key right here, is that the concentrations are constant. That's the biggest difference. Now, the question that I just proposed to you is, how would this be different if it were a completion reaction? There would be no reactants left. So how would you draw a line for reactants? It'd go from top right down to the bottom. So the concentration would essentially equal what if it were completion? 0. All right, so I'm going to actually... How is a graph of a reaction going to equilibrium different than one going to completion? Okay? You have on your sheet something, right, that has 2 graphs. Matter of fact, what I want you to do... So in completion, there are only 2 types of reactions, and I want you to write these beside the graphs. 2 types of these. Does anyone know one type of completion? There's only 2 reactions that go to completion. Acid-base. Now, what kind of acid-base? Strong. Strong acid-base. And how do we know that? Because they dissociate 100%. If you want the packet, it's right there. And what's the other type? What kind of salts?
The dissolution of the salt and water.
Let's say soluble salts. Soluble salts. Those are the 2 types. Okay? Anything else, you're at equilibrium. Anytime. Now the key there, make sure you know it is strong acid base, not weak. And we've just kind of been going through this. So when you're writing the reaction of a strong acid or strong base, what has to be in between the products and reactants? A completion error. If it's weak, what has to be between them? The equilibrium errors. That's very important that you kind of recognize that, okay? All right, chemical equilibrium, the concentrations reach levels where the rate of the forward, and again, what is rate by a simple definition? It's a change in something over time, okay? When we talk about, what is the most common rate we talk about? Miles per hour. That's a change in distance. Well, in chemistry, we talk about change in concentrations over time. So the rate of the forward, which is we're going from reactants to products, is equal to the rate of the reverse, which is going from products to reactants. Okay? Now, changes with time and rates of forward and reverse reactions. How do we know that this reaction reaches equilibrium first and foremost? Very good. That's the key. At some point, the lines flatten and they never reach what concentration? 0. What do we know about the concentrations of these 2 lines at equilibrium? Very good. The concentrations are equal at these 2 points. Okay? Now, what color is the reactant? How do you know it's red? Because it starts out. Now, notice what it says down there, the blue line. It says the rate of the reverse, which basically is going to be your product. Think about that, because the product has to be increasing and going there. So discuss the changes in rates until equilibrium is established. As equilibrium is established, the forward rate decreases much more than the reverse increases. What would cause such a drastic change in their slope? Coefficients. Remember, that's how things are going to relate in terms of how their concentrations change. It's that mole to mole ratio. So that's how you're going to have these changes. Okay? I don't think we need to practice any with this in terms of being able to write the equilibrium expression. Now, we know we have a lot of K expressions, right? There's a lot of them. KC, KP, KSP, KA, KB, KW. And they're all a little different. But bottom line is, how do they all begin? It's products over reactants. Bottom line. But the key is knowing what we put in and what we leave out. What do you have to leave out of these things? Solids and liquids. Too bad AK isn't here for that question. Okay? Also, just want to throw these things out here. Number one is that notice that the little things are the coefficients. And 2, Ks are without units. Don't worry about why. Just be excited that that's the truth. What's the one other thing that's without units that we've been working with recently? pH and POH. Don't forget about that as well, okay? All right, the position of the heterogeneous. Now, first of all, what does heterogeneous mean? It's different states of matter. Heterogeneous, different states of matter. Equilibrium does not depend on the amounts of pure solids or liquids present. The concentrations of those things remain constant. Therefore, there's no reason for them to be put in the K expression. So it is possible to have a K expression with 3 species in the reaction, but 1 in the K. Does that make sense?
Makes sense.
Okay? And then why is O2 the only thing left? It's a gas. Everything else is a solid. Now let's do a pre-think question. What if I wanted to write the K for the reverse reaction?
1 over O2.
All right, so if it's the reverse. Now, do y'all remember how I told you what is an alternate version? And I know, Joanza, y'all use these a lot.
K prime.
K prime. It's just like a little apostrophe. So K prime is just the alternate version of K, right? So what would we do if we flip the reaction?
1 over.
We flip the K. So it's just a 1 over K. Now, there's 2 other ways we can alter these things, but this is a pre-think. We're going to get to this in just a second. So again, the whole thing is make sure, and I'm telling you, you're going to see write the equilibrium expression, and you're going to get so excited. You're like, I know this. And you're not going to pay attention to the states of matter, and you're going to mess it up. So make sure when you see equilibrium constant, pay attention to the states of matter. K always has the same value unless what is changed? Temperature. The only thing that can change a K is a T. That's it. Everything is temperature dependent. But to know how it changes your K, what must you know about the reaction relating to its temperature?
Where the heat is at, endothermic, exothermic.
If it's exo or endo. That's the important thing. If you don't know if it's exo or if you don't know it's endo, then you have no clue. What is the only way to know if a reaction is exo or endo? That's it. Delta H is the only thing that will tell you if it's exo or endo. So K always has the same value to a given temperature regardless of the amounts of reactants or products. For reaction at a given temperature, there are many equilibrium positions, which basically means at this time, where is the flow chart? Like, where is the graph? But there's only one equilibrium constant. Equilibrium position is a set of blah, blah, blah. Only thing that changes K is 10. Okay. So here's a mechanism. Okay. All right. So one more time. Make sure, like I said, that you know that these are all, what did I say, aqueous solutions? Sorry, that recording thing threw me off. C. Wow. Let's try this again. First of all, since it's KC, what must they be in? Brackets. Very good. And we'll get to that in just a second about the other alternatives. So A is also in bracket and B is also in a bracket. So now, we've already talked about this a little bit, but what happened from the first reaction to the second reaction? It's flipped, right? So we know an alternate version is going to be K prime is equal to what? 1 over K. So if you have the numerical value for K, what is the only thing you have to do in the calculator? Take the reciprocal of it, and that's it. That's all you have to do. The last question on the last part of the first question on the equilibrium test that I gave you, it took the reaction and it flipped it and halved it. And all you had to do was do a little bit and you had the right answer. A lot of y'all tried to replug in numbers and recalculate the halves and all that stuff. It's very simple if you just notice that the reaction has altered in a little way. Now, what have they done in the second reaction from the original? All they did was half, but here's the important part about this one. How do you alter K prime if the coefficients have been changed? Raise it to the power of the change. So what did they do to the coefficients? They halved them. So K has to be raised to the 1/2 power. You remember that? What were be to happen if we look at the... What's wrong?
What were to be to happen?
Yeah, you know how it works. Now, what happened in the last one? What did they do the reaction?
They flipped it.
All they did was double it, right? That's all they did. So what would we do to this one? K prime is K squared. Now, this one's not on there, but I just want you to think. What would you do if we took that last reaction, left it doubled, but then flipped it?
1 over K.
So K prime would be 1 over K squared.
So every time we do the K, it's the change from the original reaction.
From the original reaction.
Extra.
Yep. Now, mathematically, I want to go back and I want to talk about the green one. In the calculator, what else could you do? Very good. You could take the square root of K. Just want to throw that at you. Don't panic if you wouldn't be sure how to do that. You could just take the square root, because anything you raise the reciprocal of, you can take the square root. It's the exact same thing. All right?
If it was like 1/4, you could take the 4th root.
Yeah. All right, this is just kind of reiterating what we just talked about. Equilibrium expression is the reciprocal for that reaction in reverse when the balanced equation is multiplied by a factor of n. Now, n is any number, right? We can just change it. The equilibrium expression for the new reaction is the original expression raised to the nth power, which basically what we just said. If you double it, you triple it, you half it, you fourth it, you eighth it, you just raise it to that power. And again, K values have no units.
Raises are usually.
What?
Raises are usually written.
Are written without units. Okay? Solving for equilibrium problems. And this is where some of you, hopefully over the past few weeks, have gotten better with this. And this is writing using ice tables and rice tables. Do you call them ice rice?
I say ice rice.
I actually call them rice E. I add an extra E. And it's basically the first E is for them to bring their math down like an algebra problem, and then the last E is the final, and this is where they solve it. It's just kind of what I have gotten used to. So again, we know that I is initial. We know that C is change. Right? Do y'all have this?
Yeah.
Okay. Write in terms of X. Okay, in terms of X. If you guys want me to send you that when and how to use rice table thing, again, I'll be glad to. It tells you exactly what to do, when, and how to use based on equilibrium question. And then E is the equilibrium. So, right here, let me change this. Only thing that can be plugged into K. Let me ask you, why are those values, the ones at equilibrium, the only ones that can be plugged into a K expression? What does K stand for?
Only.
No. What is K? What is the name of K? The equilibrium constant. Well, if it's the equilibrium constant, what should you be able to plug into it? The equilibrium values. Okay? All right. Slide. C involves concentrations. Kp involves pressures. This is something that I want to make a big, huge deal about, and I don't know if, because last year when we went to mock reading, we got in a big, huge argument about this, because what they told us is if the kids put it in just parentheses, it's wrong. They have to include the P. And that was one of the things that they gave them a point for having a wrong answer somewhere else, but they lost the point if they didn't include the P in this. So what I've told them is this is just partial pressure, so double the P's. So you have to have at least, at minimum, the P, and just include the parentheses. So if they're asking for a KP, can you use brackets?
No.
Absolutely not. So you have to make sure you include the P. And I know it's aggravating, and every time we wrote these, you hated it. But if it's as simple as writing a KP, don't cost yourself a point because you're being too lazy to write a P and write the compounds as subscripts, okay? It's too easy. Don't mess that up. All right, so problem number 1. Ooh, sorry, y'all can already see these answers. I want you to write, what all do y'all have on this? Y'all don't have the answer. You do, but if you're on paper, you don't. Plug these numbers in, because y'all will need a calculator later on. So y'all may want to kind of get a calculator. Charles got me talking wrong.
Oh my gosh.
All right, so when you write the KP for this, make sure that you use the parentheses and the P. That's the important part. Make sure you plug the numbers into the correct places. So when you plug them in, it should look like this. 2.9 times 10 to the negative second squared over those two values on the bottom. And then once you get the answer, it should be 3.9 times 10 to the... Should that be negative 4? No, that's right, because it's... Yeah, that's right. I think. All right, so we're good. I mean, you guys are smart enough to hopefully manage the calculator portion of this. All right. Now, this is something that I'm still kind of unsure of how they're going to ask this question, because if you notice, they've taken this out of the framework, I think, in terms of the calculation of conversion of KP to KC. And it's not on the formula sheet. And so they can't really ask them about something that's not on the formula sheet is how I look at it. So the only way I think that they would ask about this is if and if only this number right here is equal to 0. And here's why. And first of all, what is delta N? It's the change in the moles of gas. That's the key part that I think why they would ask this question if they asked it, is because you're just going to calculate everything. You're not going to take the time to make sure it's a gas. So it's the gas coefficients of the products minus the gas coefficients of the reactants. And the reason why I think they'll ask this, if it's 0, is because what is anything raised to 0 power? 1, which that will mean, well, what happened to the RT factor? It'll cancel, right? Which then gives you Kp is equal to Kc. So that's the only way that I think they'll ask this question. The only other thing that I want to mention to this, which R would you use and why? Why the gas R? What are you converting to? You're solving for Kp, which is a pressure, and gases have pressures. That's why. Okay, they also call this the politically correct equation. Okay, all right. Problem number 2. I think I'm going to hold off on this one, guys. Do y'all have this one on there on your sheets? Yes. The packets. Yes. All right. Again, first of all, the only thing that I really want you to solve for is delta N. See if you can solve for delta N. Sir. Okay, why is it not? What does delta mean? That's a great question. All right, give me something else.
Final minus initial.
Okay, in a reaction, what is the final thing? The products. And that's actually, I'm glad you said that. And what is the initial thing? Your reactants. So it is products minus reactants.
That's not the question. This is a question.
Really?
That's
I mean, that's the same formula, but it doesn't give you all.
That's ours.
Oh,
There's no code.
that's odd.
Why is that?
I really don't know where that came from. So we're just going to move on. So the extent of reaction, a value of a K much larger than 1. And guys, this is very simple. How do you tell what's favored in a K reaction? Let that arrow point you to the Holy Land. Okay? The point of the arrow tells you what is favored. If the point's to the right, the products are favored. If the point is to the left, the reactants are favored. Now, that's understandable, but it also should be mathematically understandable. And here's what I mean by that. So if you've got K, which is equal to products over reactants, mathematically, how do you get a value greater than 1? No, give me math talk. The numerator must be greater than the denominator. Well, in chemistry talk, what is the numerator? The products. Well, obviously that's got to be true. So if we take it and we flip it the other way, we've got products over reactants. Mathematically, how do you get a value less than 1? The denominator has to be less than 1. In chemistry, what's the denominator? The reactants. That's how you can get all those things, okay? So looking back at this, so the reaction almost goes to completion if it's greater than 1. Now, the key word here is almost go to completion. Because what is the name of K? Equilibrium. If it goes to completion, is it equilibrium? Well, duh, that should make sense. If the value is small, which means it's reactant favored, the reaction does not occur to any significant extent. You may get a little bit, but you may not get a lot. Okay? Concept check. Consider an equilibrium mixture in a closed vessel reacting according to the equation. You add more H2O to the flask. Do y'all have this on your paper? Flip over. Nope. All right, let's just talk it out loud then. How does the original concentration of each chemical, now the way they may use the word is each species, each part of the reaction, compared to its original concentration after equilibrium is reestablished? So basically means, is the concentration going to go up or is it going to go down? And then justify your answer. But here's the key part that the AP people are going to want to see. Justification needs to include the relationship of K and Q and then state the shift. And this is what I really focused on when we talked about Le Chatelier. Yes, you can say it shifts less because of this and it shifts right because of this. But they want to see, do you understand equilibrium in itself, which is a relationship to Q? Because we know Q stands for what? Quasi. Things are just getting nuts in there. Okay, we're making equilibrium be thrown off. If I hand you a bat and say spin around 10 times on your head, you're going to have your equilibrium knocked off. So that's how they want to see your relationship to this. So first of all, let's talk about the understanding of just what they've done to the reaction itself. How have they thrown the reaction off exactly? They've added more reactant. So according to Le Chatelier, it will get us into K versus Q. If we've added a reactant, how do you shift from an addition? Away. So according to this, we know that we're going to add here, so we're going to shift towards the products. So let's answer the red question in the top. How does the concentration of chemical compare to the original concentration after equilibrium is reestablished? What will happen to the concentration of the reactants? They will decrease. What will happen to the concentration of the products? They will increase. Does that make sense? Now, let's look at it from the state of K versus Q. Now, I'm just going to go ahead and show you this right here. K greater than Q, K less than Q, or K is equal to Q. Now, the simple one, the very bottom one, what happens when K is equal to Q? No shift occurs. All right, so how do we know what has just happened? So we know that Q is also equal to products over reactants. Do you agree? The only difference is one's at equilibrium.
You missed that shit.
Where? Shit up.
Watch your mouth.
Thanks, Alex. Appreciate that. Next time, keep that to yourself. Nobody knows until you started giggling. All right, so we know that Q is products over reactants. So is the addition of water an alteration to get us to Q? What part of Q was altered? The denominator. So do you agree the denominator went up? Okay? Products are going to stay the same initially. Initially, they're going to stay the same. So how does that make Q compared to K? K has to be smaller. Excuse me. Q then has to be smaller than K, right? Well, if we know that this is true, simply because we added something to the denominator, Q in relation to K has got to be less than. We'll use that mighty point to your favor. What way are we pointing now? Towards the products. What did Le Chatelier tell us? Shift toward the products. They want to see this explanation. They want to see, do you understand when you alter equilibrium, how does it compare, how does it relate to Q, and then how does Q relate to K? But what's the important part about how you relate K and Q when you write them? Alphabetical. Thank you, Jonathan. Because if you flip them, if you write Q versus K, it's backwards. We want to write them alphabetically. So if we write K versus Q, the point will tell us which way to go. So does that make sense of what the answer is? Okay. Slide tells us, Le Chatelier answer first. The concentrations of each product will increase, the concentration of CO will decrease, and the concentration of water will be higher than the original equilibrium constant, but lower than the initial amount. Read that purple and orange line again, or blue, pink, and orange. The concentration of water will be higher. Why? What did you do? You added water. Well, duh, that's got to make sense. Then the original equilibrium constant, because we've added it to it once it was at equilibrium, but it will be lower than the initial total amount. Because what's going to happen to that water when we put it in? The reaction is going to use it up, right? It's going to take it back away. All right? Students may have different answers, blah, 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 blah. So this is the bottom part, it's the important thing. K versus Q. Remember, Q is when equilibrium is off and we're adding water. Since the reactant was added, then Q, which is products over reactants, would make Q become less than K. So K is greater than Q. Let the arrow point you to the answer. We're going to shift to the products. Does that make sense? All right, see if you can do this one. Well, we know all this. See if you can do that one. All right, so you add more H2 to the flask. How does the concentration of each chemical compare to its original concentration after equilibrium has been established? Let's do the simple way first, and then we'll talk about K versus Q. According to Le Chatelier, we are adding H2, so what way are we going to shift?
Towards reactant.
So we're going to shift towards the reactants, right? So what's going to happen to the concentration of CO2? It's going to go down. But how does H2 compare to its original amount at equilibrium? It's going to be a little, it's going to go up just a little bit because obviously we're adding some to it, so it's got to go up. But once equilibrium has reestablished, what are we going to do with that H2? We're going to burn it up, right? So it's going to drop just a little bit. And what's going to happen to both concentrations of your products? Excuse me, the reactants. They're going to go up. Okay, that's Le Chatelier. That is helping us saying, okay, I know what way we're going to shift. Now let's make our Q versus K comparison to this. So in terms of Q, we know that products over reactants, which one did we add to? We added to the product. So our numerator went up in the initial beginning, which made Q do what versus K? K is now less than Q. Do you agree with that? So what way are we pointing towards? The reactants. That is why we're shifting towards reactants. So do you see how Le Chatelier can lead you into K versus Q? Yes, sir. Go ahead.
Tell the difference between K and Q again? Like, I know Q is at
K is constant at any temperature.
So,
Q is when a change has occurred. But what's going to happen if...
so that's right. If you have to find Q, then they're already going to give you K.
Exactly.
Okay, 'cause it's the same thing as-
Exactly. Okay? All right. So Le Chatelier's principle, if a change is imposed on a system in equilibrium, the position of equilibrium will shift in a direction that tends to reduce that change. There are 4 ways that we can reduce the stress. But, and over on the left-hand side, I know these are kind of a lot bigger on these. These 2 right here go together. Okay? These 2 go together. So you have to know how they are connected. How are pressure and volume related? You write this over on the left-hand side if you're on the paper. But how are pressure and volume related? Inversely related. On the left-hand side on your paper. How do you know they're inversely related?
As one goes up, the other one goes down.
Okay. If we were all running around in this room, would we collide? Let's go back way a long time ago. What causes a reaction in terms of collisions? There's 2 things.
Proper orientation.
Okay, got to have proper orientation. So if we're out there on a baseball field, softball field, if you undercut, ball's going up. If you overcut, ball's going down. We need a successful collision right there on the sweet spot. Okay, what's the second thing you have to have for a reaction?
Energy.
Sufficient energy. If you just kind of drop the bat at it, The ball's just going to fall right down on the ground. But if you swing as hard as you can swing, that's a successful energetic collision. That's what's going to get the reaction going. Now, in terms of kinetics and thermodynamics, how can we make the reaction go a little bit better? What can you add to it consistently? A catalyst, but I'm thinking of a different thing. Temperature. The higher the temperature, the faster they move, the more collisions you have, the better the reaction is going to be. Right? So, but if we're running around in here, would we create a pressure? But what if I took every one of you in here that are colliding and all of a sudden moved every one of you into that office back there? What have I done to the volume? Drastically decreased it. What have I done to your collisions? Drastically increased. So if your volume shrinks, what should your pressure do? Go through the roof, right? So that's how they're related, and that's how they're going to move, okay? So those are these. So the concentration, this is very simple. If the system, we shift away from an addition. If a component is taken away, we shift towards it. We know all that. Temperature is the big one. What's the only thing that can actually change the value of K? That's it. So K will change depending upon the temperature. But the biggest thing, and you may want to write this down there on the bottom, the temperature is dependent upon whether it's endo or whether it's exo. And how do you know if it's endo or exo? You've got to know what delta H is. If it's endothermic, what is delta H? Delta H is positive. If it's exo, is it?
Not on our paper.
Yeah, it's not on the paper. So how do you know if it's exothermic?
Delta H is negative.
Delta H is negative, and that's why I wrote that pink question. How do you know if it's endo or exo? The way you know is delta H. That's the only way that you can know. And so if we have, I'm actually going to add a slide here. If we have a reaction A plus B in equilibrium with C, and then I tell you that delta H is, let's go negative. I always like to do this. If I know that if it's exothermic, what can I add to the product side? I can add the word heat. This makes it a product now. Well, if my temperature increases, isn't that just like an addition? It sure is. So that's just like adding to the product side. So how are we going to shift? We're going to shift back towards the reactant. Okay. If I tell you if it's exothermic and I tell you that I decrease my temperature, isn't that just like a removal of a reactant? It sure is. So I'm just going to back it out this way. Does that make sense?
It makes sense, Ghost Rider.
Okay. All right. Good deal. All right. Effects on pressures. This is the big one. I don't know if y'all have this. Decreasing volume, increasing volume. We know how the pressure changes, but here's the biggest part. If you increase your pressure, you shift to the fewest moles of a gas. I know a lot of you had trouble remembering that concept. You always wanted to go, you increase to the most and you decrease to the least. It's backwards, okay? So if you decrease your pressure, you shift to the most moles. I wish I had a cool way to remember that one, but I don't really have anything that, other than the fact that it's just backwards thinking there. Okay, that's the pressure difference. Okay, multiple choice. Y'all take just a few minutes and see if you can answer. How many multiple choice questions are there? Like 4 or 5?
Like a lot. There's 3.
3. See if you can answer those 3. All right, so the first thing is consider the equilibrium above. As soon as it says that, a letter should pop into your head. What letter should pop into your head?
K.
The letter K. And as soon as you see the letter K, something else should pop into your head. What never goes in those things? So get rid of that first thing. Now let me ask you this. Can I minus be anything other than aqueous? No. We know water has the ability to be liquid or gas or vapor, so I'm assuming that this is going to be vapor, hopefully. And then it's got that other ion thing, and then it's got a hydroxide ion. So which of the following changes will increase the concentration of this thing right here? So we've got to look for 2 different things. There's 2 possible ways to increase that product. What are the 2 ways? Add a reactant or take away a product. Those are the only 2 ways we can do it. Now, yes, you can do it with temperature. Just by real quick looking, what is one thing that we can automatically cross off without any shadow of a doubt? Why E? It has no effect. Catalysts don't do anything to equilibriums, right? They just make it happen a little bit quicker. Now, let's kind of go back up to A. Increasing the concentration of OH minus. We definitely know that that's wrong, right? Because that's increasing the product. That's getting us away. So that knocks A out. All right. Adding a 6 molar, what is that thing? Nitric acid, strong or weak? Strong, very good. Now, I know what you're thinking. If I add nitric acid, that has no effect on this, but hold that thought. Increasing the mass. What have we already done with the mass of that thing? We've already crossed it out, right? Okay. D, increasing the temperature. Now, what do you have to know about temperature? If it's exo or if it's endo, but what tells us that? Delta H. Up here, delta H is negative, so that means it is a exo, which means it is a plus heat. It's a product. And this says increasing the temperature. So what way is that going to shift us? It's going to shift us to reactant. So that automatically knocks that one off. So if you didn't pay any, I honestly think you can knock at least those off. But B would be kind of where you're kind of like, I'm not quite sure. So some of you would have said there's not a right answer here. But this is where you have to know your acid-base rules as well. An acid and a base produce a salt and a what? Water. So think about that. If I add this nitric acid, what's going to happen to this thing right here? It's going to go away. It's going to neutralize itself. So if I throw some acid in, is it going to take some of this hydroxide out? Well, what way is that going to shift the reaction? Towards the products. So the correct answer there is B. Okay. Say that again. You could use process of elimination, but what if you? But I know you could have all marked A, E, D, and C off, and hopefully that would have left you with B. But I want you to know why B is the right answer. Because when you add an acid to a base, it neutralizes, producing the water, which pulls those ions out of solution. Okay? The next one, well, the answer's already plugged in. Some PCl3 and Cl2 are mixed in a container at 200 degrees Celsius, and the system reaches equilibrium according to the reaction above. Which of the following causes an increase in the number of moles of PCl5 at equilibrium? Now, where is PCl5 in terms of the reaction itself? It's a product, so we've got to figure out how to shift it towards the products. Decreasing the volume. Now, the reason I hate volume questions is because what does it really relate to? It really relates to pressure, right? So if you decrease the volume, what are you doing to the pressure? You're increasing the pressure of the volume. How do you shift from an increase in pressure? The fewest moles, right? That's going to be the hardest part. Now, how do you add up the fewest moles? What can you add up? Of a gas. Well, all these are gases. Good thing. Which side is the fewest moles? The product. So, is that going to shift us that way? Yes. So, guess what? Yay. Number one checks off. We're good. Raising the temperature. Well, it already told us that the energy is a product. Well, what way is it going to shift if we increase the temperature? It's going to shift us the wrong way. So 2 is out. So what can we do with all of our answer choices? Mark off B, mark off D, and E. So that automatically puts us at A and C. Adding a mole of HE. What is HE in terms of its group? It's a noble gas. And what do we know about noble gases? They are inert. And what does inert mean? They don't react. So that's definitely not going to do anything. So that knocks 3 off. And so that leaves us with A only. Everybody good there? Okay? Next. Which of the following changes would cause a decrease in the value of K? That should be one of the easiest questions that you see right there. Because what is the only thing that can change K? Not C, D, and E automatically off. Now you have to kind of go back and pay attention. Which one of the would cause a decrease in K? Now, what does K stand for? Products over reactants. So if I want K to go down, what do I need to make more of? I need to make more reactants. So I need to shift to the reactant side. Well, it tells me my delta H. Well, delta H is less than 0, so that's negative. So what is your type? What thermicity is it? It's XO, right? So my heat is over here. So what do I need to do to temperature to get it to shift towards the reactants? I need to increase it. So that is why B is the right answer. Any questions there? All right, y'all got about 7 minutes. See if you can answer the first question. All right, now I know that I'm just going to go ahead and show you this, but here's part B, double I think is what it is. Yeah, part B, I, and double I. It says calculate the equilibrium concentrations of the following gases in a sealed container. Well, the problem is they give you one of them in grams. Well, that's aggravating. Well, we know that if we're using a rice table, we want to try to get it in a molarity. And I know that's hard to see up there. So what I did is I converted the 3.4 grams of hydrogen sulfide. I found my number of moles. And then I divided it by 1.25 liters. That's all up there in the blue. And then the answer is 0.0798 molar. And then I plugged it into the rice table. Now, why do I have zeros in the I row for the products?
There are none initially.
There's nothing there initially. And then I have the change row. I have plus 2x and plus x. Why is there a 2x in front of H2? The coefficients matter in the C row. All right? And then you can figure it out. But what's the greatest news of this problem? They give you the EF value. That is fantastic news for you. Because now you know what X is. So all you got to do is plug in that number and go. But let's just talk because you may see it this way. Let's pretend that the value they gave you at equilibrium was for hydrogen. Now, all I would do is move it over under hydrogen. But would that be the exact value of X? What would you have to do? You'd have to half it. I'm just throwing things at you to make sure that you know how to get to X. So, we know that X is equal to 0.0372. So, what is 0.0372? Yes, sir. Did I mess up something? Oh, was it?
Yeah, it was moles.
Was it moles? Okay, I wasn't paying attention. I just looked at a number. Thank you, Jawanza. That is actually moles. So you had to divide it by what? Thank you. That is actually wrong. Thank you for catching that. Because I didn't read the question. So what is it divided by the volume? Say it again. No, what is the actual concentration? 0.0 what? 0.298. Okay. Thank you. All right, so what I did there is I forgot to change it because it does. So do you notice in one problem, they give you moles, they give you grams, they give you volume, and it is aggravating. The unit conversion on this is a pain in the butt. But the problem is they want to make sure that can you do unit conversions? Do you know where to plug these numbers in? And can you convert through them? Okay, that was my fault. I was just kind of reading off our paper and I just got a number. So make sure you're paying attention to the units there, okay? So what is 0.0298 double? 0.05 what? 96. Okay? And then what is, and this is the aggravating part, but it's just basic algebra. What is 0.0798 minus 0.0596? 0.0202. Because I doubled it. The 0.0596 is 2x. Do you see what it did? Because you're subtracting it by 2x, well, that is 2x.
Multiplying it by negative 2. When you multiply 0.0298 by negative 2. But then
And then you have to subtract it from...
from the 0.
Yep.
So it's actually subtracted.
Yep, it's actually subtracted by 2. Okay? Now, so the question is, what was B single I? What is the concentration of which one? H2S or H2?
H2.
Well, yeah, whichever order you would want to put them in. You got a question? Okay. Any other questions? Now, what is the next question actually? Calculate KC. What would you do? Take those numbers on the bottom, plug them into this thing right here, and go from there. Now, we're not going to do it unless you just want to do it. What was the value of H2? 0.0596 squared. What was S2? 0.0298. And then what was H2S? Point what? And that's squared. So do you see what you'd have to do? Now let's pretend that you completely and totally screwed up the previous problem just like I did. Let's take my mistake. Let's say that the mistake Jawan's caught me on, I didn't divide the moles by liter. I just used the moles. Could you still earn points for this part?
Sure.
Yes. Plug the numbers you have in and write an answer. You can still earn the point for this question. By the way, the black formula is the answer to part A. The red is the answer to part C. Any questions? All right, what is part D? Calculate the partial pressures of S2 in the container. When? At equilibrium. No. What does it say? Calculate the what?
Partial pressure.
This is going to blow your mind. What does N stand for? Moles. What does V stand for?
Volume.
Volume. So watch this. What? Oh, no, wrong. Okay. What is N over V? Huh. That's interesting.
That's molarity.
That is molarity. N over V. So what you're telling me is that when I say when I say P equals nRT over V, I can really rearrange it to P equals mRT. Do you see what I did? Word, right? Do you see that? So do I have the constant?
You never shared this.
Because we've never needed it before.
Hey, Mr. Richard.
You don't know that?
P equals Mr. T.
So the pressure was, what's the concentration of S2 at equilibrium again? 0.02. Now, here's the key, guys. I'm just going to write down R. Which R and why? Gas R. Why? Because we're trying to solve for pressure. But if you forget what numerical value or what your units are, how can you remember? Use that formula sheet. So 0.0821, what's the unit for the gas R? Latum over mole. Latum over, sorry, yeah, I botched the bottom. Thank you. Latum over mole. Now, by the way, does it give you the temperature? I don't.
It says 483 Kelvin.
All right, no, that's a good point. I'm so glad you just said that. Alex, say that again.
483 Kelvin.
483 Kelvin. They were actually generous. Why were they generous? They gave you Kelvin. Let's just talk about this. Why, if they gave it to Celsius, do you have to convert it to Kelvin?
Because it will cancel out the moles on the bottom.
That's the exact reason. The R unit has a Kelvin. You must convert it to Kelvin. They were actually generous in the temperature. So all you'd have to do is multiply those values, and you'd have your pressure of S2. Guys, I'm going to be honest. Anytime they ask you for pressure, you're probably going to end up using Pivnert in some way, shape, form, or fashion. Okay? But let's say that you did not, that P equals nRT over V was really equal to M times RT. Did they not give you the value of N in the problem? They told you the moles of S2 at equilibrium, didn't they? Did they not give you total volume of the container? They sure did. So you could have done it this way. But I wanted to show you a little bit different version. Okay, Alex. All right, last question. For the reaction, ooh, this is a good one. What have they done? I want you to see if you can do the last one all by yourself. Sort it for me. So H2 plus 1/2 S2 in equilibrium with H2S.
Oh,
Is that equilibrium?
This is really good.
Is this supposed to be equilibrium?
saying, guys. All right, so stop, go away. K prime,
Look, tell me that's balanced. Tell me that is balanced.
well, then it's a typo on there, because on the paper it's fine. So what have we done to the original K? We flipped it and halved it. So it's 1 over K to the 1/2 power. Or what you said, you can take 1 over the square root of K. So we had the value of K if you solve for it. So all you would do is just take K, plug it in, reciprocate it, and square root it. Parker, just stop. So, do you feel a little more confident in being able to do this?
So if they use the incorrect equation in the previous step,
Yes.
they're using that K value, they plug it in,
Yep.
or do they still earn?
Still earn a point. If so, let's say all the way back in part C, you've got the wrong K value technically, but you come up with a value, you can still get a point. You can still earn every point after that. As long as you use the same set of data, you can still earn every point. Because whatever but really you should, the way I taught them with the MRT, if they would just stick with N over V because it was exact points in there. But I wanted them to see the difference of N over V. Okay? All right.